Today's tutorial is all about second order differential equations. I'm going to look at a vibrating system and we're going to discuss that. That's question 86. And we're also going to look at the method of variation of parameters, sometimes called the method of the variation of constants. Okay? So let's have a look at 86. You're given a forced vibrating system modelled by this differential equation, where you've got some external forcing function given by 5 cosine t, and you're also given some initial conditions. Now, these initial conditions, the first one, y of 0 equals a half, would measure the initial displacement from the equilibrium position. And the second part, y prime of 0 equals 1, that would represent the initial velocity. So, just to put this into context a little bit more, I've created a little picture. Here. So here, think on the left-hand side, y is, but basically you've got a spring that hangs down under gravity. You attach some sort of mass to it, and it hangs down a little bit more. Okay? Now, this y equals 0 is the equilibrium position. That's the position where the mass would hang just normally, just under gravity. What you do is you pull the mass down to some sort of starting position and then let it go. And y of t is the subsequent displacement at any future time t. Okay? Now, our system's a little bit different though. Our system's got some damping in it. Okay, you can see up here, I've got this term out here. Now, damping could be all sorts of things. It could be air resistance, it could be some sort of oil or water resistance. And if you sit down and actually derive the differential equations involved, Newton's law, Hooke's law, and also assuming that the damping force is proportional to the velocity, you'll get this. Okay? Now C is just and K are just damping and spring constants respectively. The bigger C is, the sort of greater the damping, and the bigger K is, the stiffer the spring. So that's the basic idea in a nutshell. So how do we actually solve this problem? Well, we have seen these kinds of problems in first year, although we weren't given too much modelling information. So let's have a look. This is 86. Let's have a look at how we solve it. In this particular example, I'm going to solve it using the method of undetermined coefficients, which is just like you would have seen in first year. So it's not a huge leap from Math 1231 to solving this problem. When we do the next problem, variation of parameters, that's a bit more of a leap. So let's consider what we have here. All right, so second order differential equation. It's linear. The coefficients, here, and here are all constant. And we've got some initial conditions. So it's an initial value problem. All right, so our solution, y, is just of the following form. Think back to first year, right? It's the solution to the homogeneous problem associated with this, plus a particular solution. So y sub p is a special function that we construct based on, essentially, the form of this right-hand side. Okay? So let's solve for y sub h first. So the h means it's a solution to the homogeneous problem. By that, I mean this is just 0. right? So who can remember, how do we solve this homogeneous problem? Right, characteristic equation, that's it. So we transfer the analysis from a DE down to a quadratic equation. So this has the characteristic equation. So it's going to be lambda squared plus 3 lambda plus 2 equals 0. So we replace y double prime with lambda squared, y prime with lambda, and just y over here just with 1. Okay, so we want to solve that somehow. Any ideas? Will it factorise? What will it factor down to? Lambda plus 2, lambda plus 1, something like that. So, our roots are going to be lambda equals minus 2 and minus 1. Okay, well, so what? So now what? Well, hang on, so what's y sub h going to be? How do we determine what the structure of y sub h is? We've got these roots, these lambdas. What do we do with them? Huh? Yeah, so how did you get that? Well, the roots they're both real numbers, right? And they're not equal to each other. So that then comes up with your suggestion. So we note our roots are real. They're both real numbers and they're not equal to each other. And so the structure of y sub h is just exponentials with these. So lambda 1 and lambda 2 here would be just minus 2 and minus 1. Doesn't matter which way you put them in. Here the a and b are constants. Doesn't matter if you put the lambda 1 as minus 1 and the lambda 2 as minus 2, or switch these around, it's still an equivalent answer. Okay, so we solved half the problem. That didn't take very long. How do we find this y sub p? Well, we need to construct the solution, that y sub p, somehow. And a good choice is to look at the right-hand side of this equation and make a choice based on the structure of this function. Okay, it's a cosine function. So many students go, oh, just make my y sub p c times cosine t. No, that won't work in general. Okay, so don't fall for that. What you would like to do is say, okay, this is a cosine. What I'm going to do for my y sub p, I'm going to make it a combination, a linear combo of cosine and sine. Okay, so let me move to the next one. So that's part 1. So we're going to construct it. So since our right-hand side is 5 cosine t, I'm going to let y sub p be a linear combo of cosine and sine. Now, if you don't do this, sometimes it'll work out okay, but it won't work in general. So I wouldn't advise just going with a c cosine t or something like that. Okay, now what? Can anyone remember? What we've made a choice. What we'd like to do is determine those constants c and d if we can. So can anyone suggest how we might do that? Right. Remember, y sub p constant C and D such that this is a particular solution to this. Okay, so let's differentiate it once, twice, and sub it in here, and then we will determine the coefficients. Okay? So let's differentiate here. So I'm going to get minus C sine t plus D cosine t. And let's differentiate again. Sine's going to go to cosine. Cos is going to go to negative sine. So we're going to take this and sub into this start ODE. Okay, so that's going to replace y double prime, that's going to replace y prime, and that's going to replace y. And then we just try to get the equation to balance. Look at all the coefficients. Okay. Now this is where it gets a little bit messy. So y double prime's that. I want 3y prime, so I'm going to multiply everything there by 3. And I want 2 times y. I'm going to multiply everything there by 2. And, of course, we've got this right-hand side over here to worry about. So this all has to add up to 5 cosine t. Okay, so now what? Well, on the left-hand side, I've got cosines and sines. On the right-hand side, I've got just 5 cosine t. What I want to do is just compare the sines and the cosines on the left and make them equal to the sines and the cosines on the right. Okay, I'm going to get... Okay, this is going to give me C cosine t. And I'm going to get, what else have I got here? Oh, the cosine t over here. So I'm going to get 3D cosine t. Plus 3D cosine t. This, right? Now I'm going to add something down the bottom. As far as the sines go, I've got 2. Have I got any C's there? Yes, I've got minus 3 sine t. And I've got that and that. So that's going to give me minus D sine t. Okay, so this is all one equation down here. I think that should be a, it should be a positive, yes. So that and that gives you a positive, right? Whew. Now, let's look at all the, you can basically cancel off the cosines, cancel off the sines. So what does it mean? It means that C plus 3D has to equal 5. And the other ones are minus 3C plus 1D equals 0. So we're going to equate the coefficients to form 2 equations. Okay, so I'm going to get C plus 3D equals 5 from all the cosines, and I'm going to get minus 3C plus D equals 0 from all the sines. 2 equations, 2 unknowns. Put one into the other. Okay, so if I rearrange this one, I'll get D equals 3C, and then sub in here, this is going to give me something like 10C equals 5. Okay? C equals a half. And if I back substitute, I'm going to get D equals, just by rearranging this, 3 on 2. All right, so we've got our particular solution now. Y sub P, we assumed it was of this form, so let's just back substitute and put in C and D. Okay, looking good. What else do we need to do though? I haven't used the initial conditions yet. So what I'm going to do is I'm going to form my general solution, add the two things I just calculated, right, y sub h and y sub p, and then calculate the constants in this part of the solution by using the initial conditions, okay? So I guess this is part 3, where we want to determine our undetermined, I guess we want to determine these constants here. Okay, so that was that, and then this is my y sub p. So what I want to do now is determine big A and big B, and I can do that by using the initial conditions. Okay, so I'm going to take this and sub in t equals 0 everywhere, and I know I have to set that equal to 1/2. Then I'm going to differentiate this, sub in t equals 0, and set everything equal to 1. So our initial conditions give the following. Okay, y of 0 was 1/2. So let's go up here and set everything equal to 1/2. So this is going to give me A. This is going to give me B. Okay, that's going to give me 1/2. And that's going to give me 0 at t equals 0. So this equation then is just A equals negative B. So we don't know what they are yet, but we're going to determine them. Secondly, let's go up here, use our second initial condition. Take this, differentiate it, sub in t equals 0, set it all equal to 1. Okay, so this minus 2 is going to come to the front. When I sub in t equals 0, I'll get minus 2a. The minus 1 is going to come to the front. When I sub in t equals 0, this whole thing is going to become minus b. When I differentiate this is going to become a sine. So when I sub in t equals 0, that's going to be 0. When I differentiate this is going to become a cosine. Cosine t. When I sub in t equals 0, I'm going to get 3 on 2. And the whole thing we know that the whole thing has to equal 1. Okay, so if I rearrange this according to my calculations, I'll get this. 2 equations, 2 unknowns. This is the very last step of our general solution here. If you sub one into the other, you'll obtain the following. I got A equals 1/2 and B equals negative 1/2. So we can now go up here and write our final solution to this problem. It's taken us a while. Okay, so let's just replace that with 1/2. Let's replace that with a minus 1/2. And I've got that bit over there. Ooh. See, nothing difficult about that question, it's just long. Okay, a lot of students fall over in the exam on this question because, you know, they they end up making a little mistake on the simultaneous equations or something like this. Okay, we're not quite finished with this question. The last part says, find the steady state oscillations, that is the response of the system after a sufficiently long time. So I guess this is the last part. Have a look at this solution. What happens as t gets large and positive? Well, this is going to become negligible. This is going to become negligible, and these are just going to, oscillate in some sense. The steady state solutions, basically this will get covered up because they'll become very small, and these will be the steady state solutions. Okay, so now I'm going to abuse the notation here. This will become 0, this will become 0, and this, I'm just going to leave this. Now don't think I'm taking a limit or anything here, okay, because the limits of these functions don't exist as t goes to infinity. Okay? Okay, well, let's move on to the method of variation of parameters, also known as the variation of constants. Anybody know where it comes from? It's that man Lagrange. Joseph Lagrange. He came up with this back in the day. So not only did he come up with Lagrange multipliers, but the variation of parameters method. Now, as opposed to the previous question, you'll see with these kinds of problems, you can't use the method that we just discussed because it's choosing the particular solution that's hard in this case. Okay? So what I'm going to do one of these and we'll just discuss it. (88b). Now the method is not too far away from what you know from first year, but there's just a little tweaks in getting the particular solution. Okay, so the question asks you to solve following DE. Now the right-hand side is kind of peculiar. Now I'm just going to label the right-hand side as a function of x. So you've got some sort of inhomogeneous problem. Now, we still do assume that the solution for this problem is the solution to the homogeneous problem plus a particular solution that we construct. But the trick is in constructing the particular solution. So the y sub h is a solution to the homogeneous part. Y sub p is a particular solution that we construct. So getting y sub h is no different from what we did before. Okay, it's just look at the characteristic, analyse the roots. Are they real and equal, real and unequal, or are they complex? So to get y sub h, we are going to just turn this into a 0. Look at the characteristic equation. Okay, it's going to be something like lambda squared minus 4 lambda plus 5 equals 0. Now, with this one, it doesn't factorise, not over the reals anyway. So I like to complete the square for these problems. Okay, so for completing the square, it's all about this coefficient, the coefficient of lambda. You take half the coefficient, square it, and add it to both sides of this equation. Okay? Alternatively, you can break this 5 up in some sort of pretty fashion. Okay, and that's actually the way I'm going to do it. Now basically, half of the coefficient is -2. If you square -2, you get +4. So I'm going to break that 5 up into 4 plus 1. Now, that can be factorised. It's all about the coefficient of the lambda. Okay? So I can take that 1 to the other side. I've got a square there. So if I take the positive and negative square roots of both sides, on the right here I've got I squared Okay, so take positive and negative square roots. I'm going to get plus or minus I on the right hand side, and then when I take the 2 over, I'll get the following. Now this is just the following form. The roots are complex. In this case, alpha's 1, beta's 1. We base our solution on the fact that these roots are complex roots. Okay, so it is e to the alpha x bracket a cosine beta x plus b sine beta x. Where alpha here is just 2, beta here is positive 1. That's all right. So it's just e to the 2x, a cosine, so beta's just 1 here, so it's just cos x plus b sine x. The quadratic formula, it would still work, okay, but you just have to simplify what's in the square root sign. Okay, yeah. Okay, so a and b are just constants. We don't know what they are. We won't be able to determine them either because we have no initial condition. Okay, so that's the first part of the problem. Now the real tricky bit with these ones is actually doing y sub p. All right. Now, to construct y sub p, we actually you can use the formula, but what we actually do is base it on what we've just calculated. So I'm actually going to add another line down here. You can see here, y sub h is just 2 functions multiplied together. Added together. So say a y1 of x and b y2 of x. So in this case, y1 I'm labelling as e to the 2x times cosine x, and y2 is just going to be labelled e to the 2x times sine x. Now, based on the y1 and the y2, we're going to use those to get our y sub p. So we're basically forming a particular solution based on the 2 parts in y sub h. Okay? Now, this is where it gets a little bit different. We assume y sub p is of the following format. For the y1 and y2 that I've just labelled, we're going to assume that our particular solution is a function of x times y1 plus a function of x times y2. Not necessarily constants. C and D are not necessarily constants. Okay? And in particular, we have a formula for C and D. And the formula's here. So think of C of x as being this integral with a negative sign out the front, okay? Think of d of x as this integral here. Now, what's the f of x in these formulae? It's just this right-hand side, okay? What's the w? Anyone remember? What's this w function? Anyone? It's a special function called the Wronskian. Okay? Funny name, important function. It's just the determinant of a special matrix. Okay? So the Wronski is just this. Okay, now these are our functions. Okay, it's just the determinant of this 2 by 2 matrix. Now, from my labelling before, y1 is just e to the 2x cosine x. y2 is just e to the 2x sine x. So I'm going to replace those, calculate their derivatives, and then calculate the determinant. I guess essentially we want the Wronskian to be non-zero. I guess you don't want to divide by 0 in integrals. But having a non-zero Wronskian means that your two solutions, y1 and y2, form a fundamental set of solutions. That's important for the theory in this method. So y1 was just e to the 2x cosine x. y2 was e to the 2x sine x. So now I just have to calculate their derivatives. Now you can do that a couple of ways, just maybe using the product rule or just write it down. Here's one that I created earlier. Okay, so this is the derivative of this. And if I differentiate up here, I'll get the following. All right. So now I want to take that determinant. So to take the determinant of 2 by 2 matrix, it's this times this minus this times all of this. Okay. Now it looks a bit messy, but we're actually going to get some nice cancellation. Okay. So if I expand that, I'm going to get something like 2e to the 4x cos x sine x plus e to the 4x cos x all squared, and then this times all of this. Oh, sorry, that should be a minus. So it's that times that minus this times this. Okay, so you can see this term is going to cancel with this term, and the minus means I'm going to get hooray! Simplify, e to the 4x is non-zero for all x. Now, this is an important step in the solution. You may think, well, it's got to be non-zero because they're asking me to do it using variation of parameters. But if you don't do it, say in a class test, if you don't show that's non-zero, you'll probably be penalised. Okay? Okay. So let's go and work out these integrals. That's the last part of this question, really. Let's work out these integrals. Sometimes they're easy, sometimes they're a little challenging. Okay. So let's just write all this down with y1 equals this, y2 equals this. So let's just sub in f of x equals the right-hand side. So let's just make those changes. Now, this is my y sub 2. I'm multiplying that by my f of x, which just conveniently happens to be this. And I'm dividing by the Wronskian, e to the 4x. Okay, the second part of that, so this part here, I just replace y2, y1 and f of x and w with everything I've calculated. So it's going to be something like this. Okay, so now all we've got to do is cancel off, see if we can cancel. Well, I can cancel those signs off, and I can cancel the exponentials. I can cancel those exponentials. Can't do much about that. So, basically the integrand here is now 1. So that's a good place to be, and it's simple, right? So if I integrate 1, I'll just get x. So let's just put that out the front. And now over here, I'm integrating cosine on sine. So what's the integral of cosine on sine? Huh? Log sine x, yes. Now I don't need to worry about a constant of integration for these kinds of problems. So that's my y sub p. So all I need to do now is take my y sub h, which I got down here, add my y sub p in, and then I'm finished. So this is like part 3, I guess. Those are like multiplication.